So, my name is Daniel, and I'll be talking about the type-aware kernel virtual memory access. I will explain what it is. We'll slowly go through sort of like an introduction to the problem, to the situation, and then I will try to recreate the thought process behind creating the solution that we had with John Mark. So let's start with the architectures. So FreeBSD supports multitude of architectures. Here are the tier 1, tier 2, tier 3, and they have quite some differences when it comes to C code and how they handle data structures and even very simple types. So differences, for example, between the 32-bit and 64-bit architectures are the sizes of very simple integer types and pointers. So the same bit width as the architecture is, for example, the pointer and stuff like this. This particular difference makes it hard when people create structs, because there is the memory alignment condition that sort of creates holes in the structures, and those holes are of different size. That's like a difference. So that's not solved even by types, for example, from the standard int, because types like uint64t have different alignment strategies on 32-bit and 64-bit. Even there's like a very slight difference. So even those types are not completely helpful here. Third difference, a significant one in our case, is the character type, which is not specified by the C specification to be either signed or unsigned, and it's different between the architectures. And so there are like three distinct types, which is character, signed character, and unsigned character. So that's the third difference, and the fourth one is like the obvious, there is different endian on some architectures. So we'll get to the differences and why they matter a bit later. Now we'll jump to what is a kernel dump. So you can create a kernel dump when something goes bad, or you're just interested in the state of a system at a particular moment, and it contains all the stuff that's happening at the kernel, the TCP stuff, processes, memory management, all the buffers and stuff like this. And it's really useful to look at the kernel core dump in case of a crash, to sort of investigate what's going on. And you are able to do that with a variety of tools, such as PS, there's procstat, there's everything stat, there's ipcs, and that's like an example how to run it with the N and M options, where one of them is the executable and one is the core dump, in different file names though. And this works very well when you're sort of examining a kernel that comes from your very architecture. And the reason for that is that these tools just basically point their structures, the kernel structures, or some sorts of these structures, to the memory. And here we come to those issues of differences between the architectures, because when I point my struct from 32-bit architecture to a 64-bit one, all the memory alignment business will just go wrong, and I will get wrong data. The same goes if I just think that, oh, that's a character there, and it will have a different signedness than what I'm expecting. So all this stuff is happening, and if you try to run really, for example, PS or procstat in such a situation, you will get like a very random, or you can even like interpret it badly for these reasons. For example, the signedness. So the goal of what I'm trying to do is to add the ability for these tools to be able to examine kernel core dumps that come from other architectures, and to be able literally to take a MIPS core dump on AMD64 and be able to read, for example, the processes that were happening at the moment of the core dump. And how do we do that? Well, we need some sort of type information for that. So we need to know, there's an integer and it's this wide, and it's, this is the sign of the integer, these are the members of the struct, these are the offsets in it, and there are two basic things that provide this. One of them is CTF, the compact CTF format, and the second one is dwarf. So I'm being more familiar with CTF. I chose CTF, but it's a very arbitrary choice in this moment, because for our purpose, dwarf is just as good, because it sort of is like a superset of CTF even. And since DTrace is already there, we have the CT data generated for the kernel, so we're good to go. We already have the data. The problem is now that, so we know that there is some integer of some properties, but we got no integers to look at. Like, sort of, we just have the type information, but we don't have the data that we're trying to look at. So, we really need to starting to look into the kernel with certain entry points. And these entry points are ELF symbols, or before they were sort of like global variables in a kernel. And each symbol contains the address where it's stored, and CTF provides us with a mapping between a type that it describes and a certain symbol. Therefore, we know that at this specific address there is this type, so we can actually look at it and we can interpret the data correctly. So this is like an important part. Now, what we really now need to do is that we have a symbol, we have some sort of data, and we know how to interpret it, but we need to obtain the data so that we can later present it to the user. And for this, we sort of need to know something about our data structure that we're trying to fill in with the data that the user wanted. And for that, we again need certain type information. So when I'm trying to take that integer and fill it into my integer, I need to know what's happening so I can extend extend the two's complement notation or stuff like this. So luckily, we again have CTF, and so here what I can do is that I can create sort of the descriptions of, for example, structs or integers with CTF functions, but that really doesn't solve my problem because I still don't have the real C code that I'm going to fill in. So the brilliant idea that John Mark had was that we will have a C structure, a query C structure, like literally code, and we will, after we compile the tool, like after we compile, for example, PS, we'll run CTF convert on it, therefore generating the CTF data for our tool. And later on, during the mapping procedure, we will do a self-reflection on our own CTF data. And therefore we'll know our structures, and we'll know the target structures, so we can do the mapping. This is the grand idea of the whole thing that will be like moving around from now on. So again, it's quite. If there are some questions at this point about this very thing. Okay. So how might that look like? Like how those query structures might look like. So here is a very simple kernel structure for a semaphore, and it contains just four members. And let's say that we're interested in the last two ones, because they're just integers. It's simple enough. So we create this, shadow structure or query structure, however we call them, that look quite similar, although they can be the exact copy or they can be a subset of the previous, of the real kernel structure. And what we do at this point, we want to run the mapping procedure, which will do a very, very important thing, which is the last point actually. It's sort of like a API in a way, so that we create a contract that the members that have the same names will get mapped to each other. So the semaphore waiters and the semaphore value will get mapped here, so those will be filled in. And apart just from the member name, also the types have to match, although not completely. So when there is an integer there, I don't care very much about the size of the integer. I care about the sign, but I don't care much about that. The same goes about, for example, mapping pointers to integers. That's okay too. But in general, what I do is that I take a member and I try to find its equivalent in the other CTF description, and if it's there, I do the copying of the data. That's the mapping procedure. And also, it sort of solves the type def chains. So that means that kernel uses a lot of type defs, and what I really need to do is to solve all those type defs until I get the real type, and then I do the mapping between my query structure and the actual type. And for this mapping procedure, we implemented it into a library called libtak, which is like a type-aware kernel virtual memory library that uses CTF to get the information, the type information, and it uses libkvm to get the data from kernel core dumps or from live kernels. And the main function, and literally the most important function, and to be honest also one of the few functions there, is the map symbol function, which looks just like this, which takes a object like a handle, just like in libkvm, and it requests you to take, say, a name of the local type, which can be, for example, the struct my semaphore, as we've seen before, a symbol, which is an instance of the kernel type, and an output where it will allocate all the necessary memory and it will copy the data there. So this is the only important function that we'll be talking about and that we'll be using later on. Again, is this clear to everyone, or is there some point to explain? Okay. The mapping procedure can have a more modes of operation with regards to pointers. So either I can autofollow every pointer until I hit a null pointer, which can be a bit scary. And John Mark is very against this feature, although I find it really magic. And there's the single step, where I sort of stop I solve every integer and I solve every struct and nested structs, but I never follow any pointers. I just sort of copy the value of the pointer, and user can then call again another function from the library to continue the mapping by hand, probably like checking if the pointer makes sense or something like that in between. And it's also important in one step later on. So these are the two modes in the type library. So just like an example, how it handles linked lists, for example. So literally it just follows the pointers and creates every element until it reaches the null pointer, and the same goes for all the types that are like implicit in the definition in C language, so binary trees or any sort of any sort of tree actually, any sort of thing that sort of recursively uses its own type again. The problem comes when you think about data structure as simple as dynamic array, because there is no way in C types to denote that this is dynamic array, because it's basically a design pattern that people use in code. So there are these two members, which is usually a pointer and an unsigned integer, saying like, oh, there are these many objects, and so this has to be done exactly with a single stepping. So you get a pointer, you get a number of elements, and then you treat it, you allocate the memory yourself, and you continue the mapping inside that memory. So this is the special handling. The other way how to solve this, possibly, is to add another parameter to the mapping function, which will say a triplet of strings. First one being the struct where the dynamic array is located, and the two member names, one for the pointer, one for the integer, and the library should get the integer, read it, allocate the memory, and continue on. But this is not done. This is for the dynamic arrays, and the same goes. I don't know if you noticed a while back here, I was using int max t. and I wasn't using just integers. So the reason for this is that imagine I'm on a 32-bit system, and I'm trying to fit in a 64-bit integer. So I have to be prepared for a lot of data. So by using all those int max t's, I always have enough memory to get it in. And in case that there is like a new, for example, uint to 128 or so, I just need to recompile the tool, and it will adapt to the newest, highest variable size. But that won't probably happen that soon, or even. So anyway, sorry. Oh well, then I'm prepared. It's fine.
Int max t won't change.
And two?
Int max t can't change even if the larger range appears.
Can't change.
Cannot.
Ah. Okay.
Even if it, so it can become alive. Yes. There's no because it's embedded in the APIs.
Oh, okay. So maybe then you have to use that for such a thing, or I mean, it's not that huge of a problem. Anyway, so we were talking about integers, so that's it. That's for the shadow structures to use big enough integers. Now I will just jump off a bit to a tool that I wrote, which will come handy later in a talk, which is called ctfquery. It's one of those, CTF dump, CTF convert and stuff. So the idea behind this is to be able to inspect the CTF dataset in a way other than grabbing stuff from CTF dump. And here's how I used it a lot when I was creating all the shadow structures later on for my procstat and stuff like this. So here it has looked like when I'm, for example, trying to get the value of the type of the maximum PID on a system. So when I just query for a symbol with -s, I get the number, which is the internal CTF number of that type. And when I later run, CTF query -t with that type number, I get information that it's a type def. It references another type ID, and that's its name. And if you follow that, you will again get another type def. Those are the type def chains that I was talking about, and there is a lot of them. And it was super annoying, so I created the -c option, which is like a chain, so which resolves, if you give it a type def, it will follow all the type defs until it finds the real type, which evaluates it slowly to the type 16, which again with -t turns out to be an integer that has 32 bits, and it's signed. And the content of that is number. CTF can have void and character there in the content of an integer. So and boolean. So you know what's going on. But anyway, so this is like ctfquery, and it has been quite useful when I was. It was even faster to explore the kernel than using, for example, the fxr or just reading the kernel code. Just because of those type defs, because you really need to know what's going on. Yes?
I have a question on that. Did ctfquery with the string be told to find the ultimate? So you had to do this thing where you got 76, then you got 775, and then this thing with -c 776 to get the final value. Yeah. Is there a way to say, given a string, give me all of that, become all of it in one shot?
What do you mean now?
Can you repeat the question?
So, to find out that a PID T is an under PID T is an under 32 T is an int,
yeah,
you had to run 1, 2, 3, 4 commands.
Not really. So, well, of course you could do that, like just give me the type of the symbol, which is the 776, which is the definite information for CTF. I mean, it is of that type, which is the type they've created. But yeah, you could shorten that into like a very simple. It will do something like logic for you that it will see if it's type def and solve it.
Okay.
Yeah, it's totally doable. Although I never thought of it. It makes sense. But yeah, I mean, you just apply the same logic as you do in the -c option, and that's it. Yeah. To be honest, I tried keeping it as simple as possible, but that's a good thing. Yeah. So with this in mind, I was using all this tool all the time to create, for example, a type-aware procstat, which, just to remind you what it is, it displays information about processes. It works in certain modes, so there is a mode for security, the general mode, file descriptors, network, command line environment, and each mode is comprised of certain data columns, and each row is a process. So that's like what procstat has, PS basically, a bit nicely defined. So in general, for all these tools, there are 3 steps that you want to do. You want to understand what the user wants from you, so that's like parsing the command line options. We don't really do that right now. Then you need to obtain the data, which is our part that we are trying to do, and then you need to present the data, which again we can skip for this talk. Although it was part of the Google Summer of Code stuff, but it's not that important for the talk at the moment. So now we want to talk about procstat shadow structures. So the entry point, the symbol, the global variable that we are going to use for this is the allproc symbol, which has also a friend, the zomproc, which is for zombie processes. So this is basically a linked list of all the processes, or the symbol itself is just the head of the linked list, which is the one that you can find in sysq.h. So as an example, how that might look, I will now go to the GitHub code of the tool. Yep. Okay. Yeah. So what happens here is I believe this is the one. Yeah. So these are the mapping structures that I've created for the procstat. So here's the lowest one. The PS procstat is just the head of the list, and it points to a first PS proc, which is basically again like from that I want PPID. I still have to, as I said before, the API. I still need to keep the member name, and I need to keep sort of fuzzy the type the same. And there's also arrays which are also supported by the mapping structure. And sort of like my own subsets of, for example, the credentials, so or the usage of like the resource usage. So there's again the time wall and stuff like this. So all this you could actually look at as it's quite. The advantage here is that you can actually see like what you're requesting, and it feels very clear to the eye, like what is it that the tool is actually doing, and what is actually requesting from the kernel, and how would you use that is the main. So here we will use the. We're doing some parsing, I guess. Yeah. So here comes the main function, which is the tag map sim, where you get the connection, and you specify the name of the local structure, the name of the symbol, and the place where you want to put in the data. And if that's okay, if you get the tag okay or not, then you report. And after that, you just walk the list just by following the pointers that you already got, and you fill it to a one of the libraries that I wrote for you, which is like a table layout library for command line. So this is it. I mean, this literally does the basic procstat stuff, and it's super simple. I mean, there is not much magic happening in the tool itself. All the magic happens in the one function, which is the tag map sim. So that's really interesting part, and then you really see what the structure, what the utility is doing. The thing is that it is really a prototype. So there aren't all the modes implemented, there aren't all the columns implemented, but that's just a matter of creating more and more of those query structures, and that's basically it. And it goes for all sorts of tools. The same goes for netstat, where you just start looking at the TCP info and you work from there. Or you can list the zombie processes with the very same code. You just replace allprog with zomproc. There are other things for you can do the same. Like you can create a jail stat, which will look in the list of jails and get for example the IP for address of the jail or something like this, or just the jail ID. So what this enables is that you can look at the kernel code. Look at the data you would like, and just write those structures, find a entry point, and connect that all together to have a completely new tool in a very easy manner. Yeah, is this clear how this works, more or less? Or are there any questions regarding this? Ooh. Yeah, I see. I guess it's
the other room then.
Slowly. Cursor. Well, anyway, yeah. So until it loads. So what are the possible other tools? I've already said that, for example, the jail stat or re-implementation of all the tools that are there right now. It sort of has an impact also on the kernel code, because currently there are, if I'm correct, all the k-info structs, which are for a very similar reason there, to sort of provide like a wrapper around the actual structures, which could be literally replaced because they are linear in the way they are, because every time you have to create a new k-info in a kernel, and it's not really supposed to be there because it's working with a tool. So that structure that you are like using to get info should be in a tool. Correct me if I'm wrong on this.
By the way, I think you want to unplug and replug your.
Yeah, probably. Yeah. It will take some time, but we'll be okay. So, going back to the presentation. So here is some work that can be done apart from, as I said, this is like really a prototype-ish sort of thing, and there are lots of ideas on top of this. First one, and the idea comes from the fact that those tools are not connected to a particular kernel version. They are just connected to the types that the kernel version uses. So it might be that, for example, in procstat, in an older version, there won't be one particular column, but you can still render the rest. So the mapping function should also return certain metadata that the tool could use. If there is no PID, well, probably that's like a failure for the utility. But if there is like a missing column somewhere, well, you just go with it and you don't display it, or you display like question marks there. So what can be done here is a continuous integration. We need to go deeper. So you can actually check if a tool is requesting certain types and members to be as it expects, and you can see that, oh well, you have made a change that will break the type-aware procstat. So you probably don't do that, or fix the tool in some way. Exactly, the missing and changed members reporting, and the same goes like how many versions back can we actually use this tool. The other thing is that you can have multiple sources of the type information, as I spoke before with the dwarf, and you can have multiple sources of the data actually. So imagine using this with a DTrace on a running process, or with libelf for a process core dump. So this way, imagine you have a Firefox from a different architecture that you can actually get some information from on your architecture. Which, I mean, Firefox might be a bad idea, but like imagine MySQL instance or stuff like this. So all possible combinations can be created. Like you can use dwarf and elf or any other thing, and the tag library is prepared for this. So it should be easy to plug in other sources of data and other sources of type information. And yeah, like you can create custom debuggers or custom stat tools for example, MySQL core dumps, yeah. And porting it to other kernels, so just like, you know, for example, OS X kernel has an allproc and TCP info, which are super similar according to the CTF data there, and basically there is no restriction, like it's not necessarily only FreeBSD thing, although CTF seems to be, at least for now, like a very FreeBSD thing. So yeah, there is a lot to talk about, I guess. So from my point of view, I mean, that's the basic idea. And you've seen the code, and you've seen how to create those tools. And I guess it has a certain impact. Making it happen and going for such tools would have an impact on the system. So I guess I'm interested in a feedback of what you think about this, in a sense of, you know, like removing the older tools or keeping those as like TA procstat or something like this, as a symbiosis or something like this. I don't know, but that's it. Thank you.
Gorgeous. I had a question, Joe. I'm also going to force the audience to ask questions. So, are there any questions from the audience before I just ask Daniel or Shirley questions? Is anyone awake? No. Okay. So I'm going to stand here and ask Daniel questions. I feel like I'm interviewing you. So the first thing is, this is a summer code project for us.
Yes, yes.
When are you planning to integrate the code into the tree?
Well, it's quite prototype-ish, so I don't think it's quite ready for the tree.
So when are you planning to integrate the code into the tree?
That's a good question.
I mean, have you talked to John Mark? He's the person who...
Yeah, I mean, we spoke, and for the last like a month or two, he was sort of very quiet and non-responsive. And then actually, I asked more people here, like, what's happened, nobody knew, but it just happens that John Mark is quiet at the moment.
Okay. There are others of us who can help you integrate the code into the tree. And what about, do you want to add ctfquery to the tree, John? Yeah. Put it into the tree.
Well, it can be as a package, I guess.
Or in with the rest of the CTF tools.
Yeah, too. Although it depends on my libctf, so that would have to be into.
See, so when are you going to integrate that into the tree?
Yeah, that's quite easy. I mean, that's already sort of done.
So, and if you wanted to convert it to use dwarf, how much more work do you think that is?
A week, I would say.
Okay.
A week. But the thing is, I mean, we spoke about this. I think that it is possible to make the CTF, libctf, to read dwarf as a sort of source of information, and yet still be able to ask for that information through libctf.
Okay.
So
that's probably the right answer, actually.
Yeah, well, true, because then you can replace the one in DTrace.
Yep. Which is what we want to do.
Yeah, with it can still look like CTF to DTrace, although the data will come from dwarf.
And so you kept saying this has an impact, but what do you mean by that? Just the
for example, removing the kinfo structs, I guess, removing the older versions of those tools. Okay. And I know there is like a libprocstat, I think written by Robert. Or, yeah.
I don't remember who makes it.
Yeah. So I mean,
you don't mean an overhead. You don't mean that it has a runtime overhead.
No, not really. They are quite, for example, resolving pointers and stuff like this is like with a prefix tree, so it will be constant for any pointer to
look up.
Yeah, exactly. Okay. So I mean, it's performant enough to be like a real-time refreshing of things.
And you're depending on either the dwarf or the CTF info. It's already in the kernel. So the kernel doesn't get bigger when you use these tools because you're depending on the data that's already there.
Yes. The kernel is just there, and I'm just sort of reading stuff.
And of course, when you talk about doing something like grabbing a Firefox from another architecture, but you still have to build Firefox with CTF information to get that out. Or you can look at the dwarf. Yeah. You still have to have some debug information for it, which can be separate, I guess. Well, look, we have an actual question about that interview.
coming from a NetBSD perspective, we have quite a lot of architectures where DTrace at the moment is not supported. How much does the CTF infrastructure and your work actually depend on platform-specific data?
So it doesn't. So CTF was created a long time ago by Mark Shapiro for MDB, and it's like a very separate thing. And just because he was at the same office with the DTrace people, I guess they used the same. So it's separate from DTrace and separate from MDB. So just like compiling my libctf is easy, completely easy. I mean, it's some C89 written fairly as standard as I was able to write it.
Well, LibB is also pretty much standard C++ and needs a lot of porting for every new architecture, so that doesn't say much by itself, yes.
Yeah, the code is small. It's small compared, for example.
Well, and I think the other way to answer that question is you're thinking of the things that make DTrace work, which are platform specific. The CTF itself just has to know about types.
That's kind of what I'm asking,
Yeah.
how much is
So,
really x86 specific.
Yeah, because if you looked at porting DTrace, then you have to have a bunch of, you always have to have
Yes.
architecture specific code. CTF has far less than that.
Not
It cares about the size of things, 32
Yeah.
versus 64.
Exactly, yeah. I mean, it's fairly simple as far as anything else goes. Yeah.
Other questions?
So if we integrated your procstat, would that mean that we would lose the ability to get information out of a kernel without debug information?
If you remove the k-info structs, yes.
Yeah. So it seems like we probably want to preserve that ability, particularly for, say, embedded devices where you might have installed it on there, you might have lost the debug info because you didn't put it on the SD card or whatever, or in the flash. So we might want to preserve that ability to both look to query that and use the k-info stuff, even if we don't do it as the primary method.
And I think we also need to keep k-info to do things like post crash code. Right? Would you be able to? So if I've got a kernel, actually, yeah, I guess if I've got a dead kernel, I can still look at those tools.
Yeah.
I guess they will.
Actually, what you can do for embedded deployment is we have a similar problem on NetBSD with a symbol table where we want to get a symbol table into the kernel to be able to do backtraces and the like, and the embedded loaders have no way of loading that, so we put it back into the kernel. And you could do similar things with the type information by extracting the interesting types directly from the intermediate kernel image and then strip them off and put them into a special data section or so. So.
Other questions? Yes.
Does FreeBSD have dynamically loaded modules, kernel modules?
Yes.
Does FreeBSD allow those modules to implement the sysctl?
Sure.
Yeah, any executable can have literally any.
If yes, if you load some kernel module and if it implements sysctl, you have to load associated metadata, type data at runtime.
Yes, well, the CTF itself is a date on disk, so it's like just a bunch of data. It's one of the ELF sections. So just like the kernel module is an ELF object, it will contain sections, and one of those will be the CTF data that is sort of generated from the code of the kernel module.
So,
and then you are able to look into that. Like you are able to create mapping structures with those CTF structures.
It's at runtime, not at compile time. It's put in some directory. I don't know, you share somewhere, and if you execute some program, it dynamically reads all of these zones.
So when you do KLD load, you're loading an object that has the debug information, the CTF information, and the code into the kernel and then linking it at runtime. So all of this information would be there. You don't have to do anything special, right? Because otherwise you wouldn't be able to debug kernel loadable modules. Does that answer your question? Yeah. Okay. All right. Any other questions? Thank you very much.